Now we're at chapter 4. We're going to go with discrete probability distributions. English, the word discrete. What does the word discrete mean in English? Anybody heard that word before? Anybody said that word before? Okay, discrete means not out in the open, right? It means kind of like off to the side, right? Being discrete, not for the whole company, right? In mathematics, that's not what it means. Okay, discrete mathematics means it doesn't make sense to do like half of a number. So it's like you're counting things and just that count makes sense. So number of children in a family, that'd be a discrete kind of thing, right? You can only have one child or two children, not weird to, it's kind of weird to have 1.5 kids, okay? So there's that, as opposed to how much time it took to do an exam, right? That could be down to from hours, right, to minutes, down to seconds, down to milliseconds, right? That is, it's called continuous data, right? You can kind of stretch a line. So again, in your mind. So chapter 4, we've done all the stuff in chapter 3, but we've done stuff with continuous data. Now the question is this: what happens if I'm having data that's like 1, 2, 3, 4, 5, right? That's what chapter 4 is about right here. That's it. So discrete data. How do we do probability for that kind of data specifically? So 4.1, probability distributions. That's cool. Something called binomial distributions. And then we've got the more section. Anything else that the author could throw into 4.1 and 4.2? Okay, probability distributions, here we come. So first things first is a random variable. So it represents the numerical value associated with each outcome of probability distribution. So that's kind of like, what does X mean? Right, in algebra we did that too, right? What does X mean, especially word problems? So we'd say X means the length of the rectangle, right? So in this case, same thing here. It's going to be denoted X. It's like, what are you trying to find? That's the question. We do that a lot in mathematics. We say X equals, what are we trying to find? That's the whole point here. Okay, so now let's talk about the word discrete just real quickly here. We have it in our heads already, but just for us to note. And I still see people writing, so I'll just wait just a little bit. No problem. All right, so difference between discrete and continuous. Here we go. Discrete random variable means has finite or countable number of possibilities, and they can be listed. And what we normally do is we make a lot of stuff discrete variables. That's what we do, because it's a lot easier to compute those than not compute those. So it has a finite, well, we can count them. And a lot of things that we count. Remember, we just did the homework problems, right? And we counted the heads and tails, right? Is that discrete? Absolutely, right? There's only 4 different possibilities: head, head, tail, head, head, tail, and tail, tail. So that would be considered discrete variable. Okay, another one. Don't need to write this down, but just an example here. it was example of sales calls a person makes in a single day. Right? Once he picks up that phone, once he dials it, that's considered a number call, right? At that point, you can track that, and it is discrete. You can't make 2.5 phone calls. Okay, the other side. The other side is called the continuous random variable. Continuous means it continues. It continues and continues. So this one, you can't count them. Usually what we do by then is we just represent it by an interval or a number line. So we can't count it, but I know it goes from maybe like 1 to 7. Just anywhere between. And so recently for me, how about that? The tread on a tire, right? Even though they do scales of them, right? The tread, if you start counting inches, right, that would be continuous. And so this is a good example. We make something continuous into something that's interval. So what they do is the person, when he measures the tire, he says there's a scale of 32 pieces. So anything from 0 to 32. You guys have seen that ever replaced your tires or anything else like that? No. New world over here. Okay. So when you walk into a tire company, they look at your tires. They have this little meter. They go to a thread of your tire. They push it down. And they say, hey, look. And the highest it goes is 32. The lowest it goes is 0. And they just give you a number between 0 and 32. Once it's like 10, it's like, you better replace your tires. Anyways, that's a good example. Because inches are just inches, right? Millimeters are just millimeters, right? Yeah, correct. But it's divided into 32 pieces, right? So it's like a scale. So like if you count in millimeters, that would be continuous. Once you put a scale of 32, now you just made it discrete. Okay, so here it is. How about this? Hours spent on calls per day. Now that could be continuous, right? You could spend 1.4 hours, 1.327 hours. So notice that we're still talking about sales calls. We're still talking about that, but it's the number makes it discrete. Hours spent just made it continuous. So something very similar could be one or the other. Okay, let's do 2 examples. Don't write these down. Let's talk to me about this one. Here it is. Determine whether each random variable X is discrete or continuous. Go for it here. Let X represent the number of Fortune 500 companies that lost money from the previous year. Go. Discrete or continuous? Ooh, starts with a D. Discrete. Because the number of Fortune 500 companies, can I have 3.4 companies that lost sales last year? Or does it have to be like 3 companies? 5 companies? Yeah, it's going to have to be like a single certain company name. So discrete because they can be counted. It's going to be a scale from 0 to 500, and they're going to be counted individually. The number's going to be individual counted. Okay, number 2. Let X represent the number of gallons in a 21-gallon tank. Go. Continuous, right? You can have 2.7 gallons. You can start measuring these gallons out to the 20th decimal point, right? You can have 10.65873 gallons. So it is continuous. It still has a beginning, right? And it still has an end, right? But it's still going to be continuous because I can divide those gallons out. Okay, so now let's go with this one here. So the conditions for a discrete probability distribution. This is what has to take place. Discrete probability distribution says I'm going to have to list all possible values of this guy. Second of all is this. It must satisfy 2 conditions. One is this probability of each of the values has to be either 0 to 1, anywhere in between. right? If we only have 30 items or 30 data points, you can't have one class that has 34 data points. Doesn't make sense. All these data points are going to be between 0 and 1 for probability. The second thing is, when you add up all the probabilities together, it's better equal to 1. Lots of writing. I'll wait for it. Technically, we actually have done this before already. We did chapter, I think it was chapter 2, when we did those classes. And we had to figure out the probability within the class, something super, super simple. So 2 things that must be satisfied if it's a discrete probability distribution is all the probabilities between 0 and 1 inclusive. Add up all the probabilities you have to get. All right, so I kind of did it 2 different ways here, depending on which way you're comfortable. Maybe both here. If words is on the left, symbols themselves is on the right. So P stands for probability. X means for the event. So P of 2 heads or 2 tails. Probability is between those 2. Remember that little guy right here? You guys talk to me. What does this little guy mean right here? Sigma. Good. That's cool. That's sigma is the Greek letter, the name of the Greek letter. It means sum, right? Add them up. We use that Greek symbol for adding things up. I think we're all good. I don't see anybody else writing here, so let's go through this here. Let me jump to this one. Let's go to this one as an example. So here's what we do. We're going to construct a discrete probability distribution. First things first is we've got to figure out, are these discrete, is this discrete data? Industrial psychologists administered a personality inventory test for passive aggressive behavior. Oh, none of us have that. 258 different employees. Each individual was given a whole number score from 1 to 5. So not 1.2, right? You got a scale score 1 to 5. 1 is extremely passive, 5 is extremely aggressive. That's cool. 3 means neither trait was exhibited. Results are shown. So first things first, is this the discrete data? Yes, you can only get a score of 1, 2, 3, 4, 5, right? Okay, and then we have all these guys here, 24, 33, 34, 31, 32, and 24. Okay, can we do this? Can we construct a probability distribution for these guys here? So if you don't have your notes, right, if you have it printed out, can you copy this table down really quick? And then make another column. Just make another column after that. So make 3 columns if you can on your sheet of paper, 3 columns versus the score. Next would be the frequency, and just copy this down. And then make 1 more extra column right over here. Extra column, a 3rd column. And I'll tell you what to label it in just a bit. And put in both columns. Put in the score column, put in the frequency column. Put in the 24, 33, 42. All right, and then let's see. Then let's construct the next one. So the next one is going to have, we're going to go sideways right here. Sorry, guys, we're going to do 2 different things here. So your 3rd column is going to be this P of X. Good. So on your notes, because you guys have had it correctly, your 3rd column should be labeled P of X. So this is the probability. 3rd column P of X. So have 1, 2, 3, 4. Right? This is going horizontal. This is going vertical. That's okay. So now the question is, what's the probability of the person having a passive aggressive state trait of 1? How many people in the survey? 150. How many people just in with the score of 1? 4. So let's take out calculators real quickly here, and let's go with P of 1 would be 24 divided by 150, which is 0.16. Perfect. You're going to write that into the 3rd column, 0.16. Just the decimal. This was called, let's see, in chapter 2, we called it relative frequency, right? Relative frequency. Same exact thing, same exact computation. We just have to think about it in our minds. These are discrete data sets, right? Not ranges. Cool. Okay, next one is all yours. Go for it. Can you fill out the chart here? Ooh, some people already halfway done. That's cool. What you guys get for the next one? 0.2 is perfect. I'm going to look on another person's paper here. 0.28 is the next one. Some people are actually writing what they're doing, right? They'll actually write 24 divided by 150 equals 0.06. That's fine too. Just so you remember for later. Okay, I got 0.20. And now the question is, do you leave off the 0 at the end, or do you make it a 0? In statistics, we like the numbers to be nice. And so if you want to put an extra 0, therefore everything has 2 decimal places. That's just the thing we do. And 14. So your number should be just like that. So. Okay, are we good? Yeah. So, jamming, that's awesome. Anybody not good? Okay, next. Don't need to write this down, but let's think about it here real quick here. If we are to validate if this is a probability, just a discrete probability, we have to do 2 things, right? You guys tell me what the first thing you got to do off the notes. First thing was off the notes. What's the first thing we have to do? You can read it if you like. That's fine. Probability of each of these values has to be between 0 and 1. True. Is that true or false? That's true. That probability, each of the probabilities are between 0 and 1. Awesome. Next, do all the probabilities add up to 1? Now that's a check you guys have to do. Go for it. Add up 16, 22, 28, 20, and 14. Before it says yes. Anybody else? With a yes, says you're adding up. Good, I got 2 yeses. I'll wait for a third yes. Awesome. Okay. So between 0 and 1, yes. All of them add up to 1, yes. We've got ourselves a discrete probability distribution. Next is graphing. Graph this one. The graphing is going to take place just like the frequency distributions we used to do. You guys remember that stuff from a long time ago? Okay? So nothing new. I'm not sure if they want to graph it as well or not. Up to you guys. But I think we had practice with it in chapter 2. Just note, I guess, a few things here. First is notice it starts off with 1. And so these guys are called midpoints. Remember that? Midpoints are the middle sections. We usually do that for discrete probabilities. We don't do borders anymore because it's not continuous data. Good. Next, the Y scale is your probability, and you look to see which one's the biggest one. So 28 is the biggest one. So maybe I'll go out to 30. That's fine. I'll go out to 30. Do everything by 5s. So there it is. So interestingly enough, so according to this, I'm not sure if it's real data or not, most likely not. But it looks like most people don't exhibit one or the other, or at least 30% of the population exhibits none or the other trait. Interestingly enough, how about this, guys? 28 plus 20. So about what, 22% of the population? About 20% mildly exhibit one of the traits. We're good? And 16 plus 14. 30% of the population, right? Exhibit those traits. That's the 2 people you watch out for. Okay. Are we good? Let's see where we're at time-wise. Let's check. Sometimes things are not discrete probability distribution, even though they look very much similar to it here. So this one right here, don't need to write it down, but tell me yes or no. Is this a discrete probability distribution? So this is verify the distribution. This is a 3-day forecast. So today, you got a 21.6% chance of rain. Tomorrow it's about a 43.2. The second day, 2 days from now, and 3 days from now. Is it a discrete probability distribution? Okay, hold on. Let's talk about it because this would be good to talk about. So first things first is a 3-day forecast, right? Let's say it actually was raining for the next 3 days, right? Today it's raining and the next 3 days it's raining. Wouldn't the probability be like 90%, right? 90%, 90%, 90%? Okay. Is it talking about, do these 3 or 4 days, do they hold all the possible outcomes of an event? No, right? We're not here. We actually are not even talking about outcomes whatsoever, right? We're talking about a forecast. Good? So even though the probability distributions are, yes, are between 0 and 1, I understand that. If you add them up, do they give you 1? Yeah. So they fulfill the criteria. I totally understand that. And it goes against everything I just said. Because on the next slide, it says this right here. Because both conditions are met, the distribution is a probability distribution. I am going to disagree with the text for this. Good. Because that has nothing to do with outcomes. It has nothing to do. It meets the 2 criteria. So I'm going to check on that again. Yes, it meets the 2 criteria, but it's not a distribution whatsoever. Okay, let's go on. Okay. Let me look at this one here. Okay, this one, again, we don't know what the context is about now, right? It's just numbers. At this point, then you look, because there's no context. So then, yes, do they add up to, are they all between 0 and 1? Yes. Do they add up to exactly 1? Anybody check real quick? No, it adds up to 1.07. So no, this is not a probability distribution. Next. Again, not writing stuff down, just kind of think with me. Yes or no for this one? No, what fails? 5 over 4 fails, that guy's bigger than 1. And this one also fails, that's a negative. Even though actually if you were to add these guys up together, it would give you actually a 1. Just kind of random numbers that fail. Okay, number crunching, here we go. Now we got some mathematics that we're going to start doing. You guys talk to me if you guys remember. Do you guys remember getting the mean? Getting something called variance? Remember variance from a long time ago? And then getting something called standard deviation. Do you guys remember that? Man, I remember standard deviation. So guess what? We're going to have to do the mean, the standard deviation, or the variance, and eventually standard deviation. Well, actually, no, standard deviation right away because we don't need to look at variance, because variance is just a square of standard deviation. Okay, so what do we do here? This means this. This means that in order to get the average, this is kind of cool. So the average or the mean of a discrete probability is that you add up all the x's and you multiply them by the probability as well. So you multiply the x value and the p of x value, and then you multiply the next x value, the px value, and then you just keep on adding them together. That's what that means right there. Okay, so let's work with our table over here. So off to the side, it's the same exact table that we had before. Here it is. There's your table. Question. Are you guys going to do it? Check with the neighbor next to you. Can you multiply the x value times the 0.016 value, and whatever that multiplication is, make a fourth column over here. So we're going to make a fourth column. We're going to add it up, just like we did for standard deviation last time here. So I think it was this. Now we're going to make another column called x times x. Let's talk to me here. What are those numbers? Those are the top ones. 1 times 0.16 is 0.16. Okay, fine. I'll do another one for you. 4 times 0.20 is 0.80. Okay, 0.44. Perfect. Sorry, let's see. Take a peek. I'm doing a accumulated. I'm doing a. I think in chapter 2 we did this with the midpoint, right? And the midpoint times the frequency. Not accumulated. Accumulated means you just keep on adding the numbers on. Okay, 3 times 0.28 either. 0.84. 0.84, okay, and then 5 times 14. 0.7. 0.7, exactly. Okay, then I need the summation right here. Two point what? 94. Awesome. So notice real quick here, this is so interesting. I don't need to divide. Remember how you used to divide this number by how many we had before, right? But because we have the distribution, it's a probability. We technically already divided out, right? By doing the probability, we already divided out by, what's that, by 150, right? We already divided out by 150. So off the side here, we can try with this right here, the mu or the average is four. Okay, so we'll come back to this in just a bit, okay? It is so interesting because remember for the average last time, we had to do an extra little step, right? We would add up all these guys, right? We'd add these up, and then we would divide by how many we had. So that little dividing step of dividing by 150, we don't need to do anymore. Good. We already divided each of those by 150. Did you guys use a calculator today? As of today, did you guys sometime during this problem divided something to get divided AB by 150? Yeah, remember to get this little column right here, right? To get that column, then we divide by 150 each time. So because we divided by 150 already, we don't need to do that again to get our average. We get it once. Double probabilities. Okay, standard deviation. I know that. Let's see. Hold on to this one on your notes. We're good. Let me jump to somewhere, and then we'll jump back to this. Okay. So let's go to definitions here. So here it is, variance. Variance and standard deviation. We'll do the formula for it, and then we'll actually do it on our notes. All right, variance. Notice also that we don't need to divide by. If you go back to chapter 2, chapter 2, you find out that, hey, remember a long time ago in chapter 2, when we were trying to figure out variance and standard deviation, what we did is we divided by how many things there are. We divided by n. Remember dividing by n? We added them up, right? And then we divided by n, and then we took a square root. Okay. That's variance. Variance is cool. And then we have the standard deviation. That's the one we normally use. So it's the square root of the summation of the differences of the values themselves and the average times the probability. And that probability technically has the 150 division. Okay, so guess what we got to do? We have to figure out. We got to figure out this one, the x minus mu first. Once we figure that one out, then we got to get a square form to it. Then after that, we have to figure out a way to multiply the summation of the probability times that. So we good? Take a little while, but we'll get there. Remember standard deviation in chapter 2? It was a long time, right? Do that, and multiply that, and we multiply itself, and square it, add it up, so it's a little bit. Okay, so let's go back to our previous slide. There it is. So I have mu, so maybe the next one will be x minus mu. That's what I'm looking for. Once I have that, then I'm going to remove this guy. Okay, the equation is on top. That's cool. So now the question is, what is 0.16 subtract 2.92? So let me write down the formula for the first one. Let me write down the numbers for the first one. So 0.16 minus 2.4 goes right. Okay. All right, can we do that calculation? Say again, negative 7.8. Speak just a little bit louder because wonderful masks that we have distort sound as well. Next one, over here. Negative 2.782. 2.718. 72. 72. Thank you. And then rating it also, if you're not getting the same numbers, then you got it. Yeah. Are we subtracting by p of x or x of x? X minus mu. All right, so 0.84 minus 2.94. Real quick here, just in the subject.
For the second one, negative 2.5.
2.52.
Negative 2.5.
Gotcha. Okay, we are reshifting this right over here. Gotcha. Okay, I'm going to put an extra 0 there because that means all the numbers have 3 digits and stuff. Yeah, it kind of just looks better. Sorry, go ahead. Tristan, good. Negative 2.1. 2.1. Okay, perfect. I'm going to edit next to 0, so it has 2 decimal places. Actually, negative 2.14. Okay. And okay, almost there. Okay, so just kind of double check those numbers, just make sure we got it. Then this one's going to be x minus mu. Second power. So now we're just squaring these guys over here. Negative 2.7. Remember, come on, let's talk about this here. What did we do with the what did we do with the negative? Remember we were doing this last time? We squared it. There's going to be no negative. So if you want to square this, you should just type it out again. Forget the negative. Just put 2.78 squared. What is 2.78 squared? 7.7384. Okay, I don't have the numbers in front of me, so you guys have to be my guys to check each other.
Wait, how do we find that first one?
Sorry, how do we find the negative? 2.78 times 2.78. 2.5 times 2.5. Good, yeah. 6.25. 2.1 times 2.1. 4.41. 41. Perfect. Good. 2.14 squared. 2.5796. Okay, and 2.4. 5.0176. Okay, and I just need to verify those numbers before we add them. Anybody got anything different? This is why a lot of times when you're doing statistical studies, you usually do it in two. Because one, you just want to change the smaller number different. Which one? 4.14? 2.14 times 2.14?
For the for x, for the squared one should be
96 is at 86.
Yeah. 25796.
579. Before that we were saying?
No, I got 4.
After this one?
Yes, I got 4. I got the same thing, but 4 to my sister.
Oh, got it, okay. And what was it, 2.14 times 2.14, it's 4, right?
4, yeah.
Yeah, that's why, that was me, most likely, looking at the 2, writing down the 2. So it's 4.5796, good. Yes, that's good. Okay. Thank you guys, thank you for helping out. Brian, thank you so much for getting most of the answers, that's cool too. Real quick, just before we start adding things up, real quick here, let me tell our average. Notice our average was 2.94, right? Our scale goes from 1 to 5, right? So the scale from 1 to 5, that means the middle is a 3, good? And our average was 2.94. That makes sense, right? Average would be like about 3 or so, right? And notice that the scale is just slightly less than 3, right? So that means, where's the sample? That means the sample people were slightly less aggressive, right? So more passive, just barely, right? It's not a 3, but 2.94. The average is a little bit further down. Okay. Anybody got this? Hold on, wait. Do we add this stuff? Look back to your formula for what is your formula? Formula says what? Do you add up the x minus mu squared, or do you multiply times something first? Yes, you gotta multiply by p of x first. Oh man. All that word. I can't believe math. So x minus mu squared times p of x. These numbers are gonna make this get bad. I will tell you. Okay, so I'm gonna go, am I gonna go forward? One second, let me check something out here. One second. This is all. Okay, guys, let's do it. It's not gonna be fun. We've got to do this here. So we're multiplying this table and this together, right? They're pretty small. So if you guys write it down, I think I need more paper here. So let me take out this right here. Let me insert a whole new paper. Okay, so I'm making my column here. Column is listed as the summation, just x minus mu squared is x. How many inputs? 1, 2, 3, 4, and then the summation. Okay. Help me out here. Let's go for it here. What is 0.16?
1.236544.
Oh man, that's not gonna be fun. 77284. Right, say it again, please.
1.236544.
Yes, thank you so much. Anybody want to see if that's correct? Okay, check with your neighbor as well. When you do the calculation, check with them to see if they're doing it correct.
Yeah.
Okay, cool. And the second number.
1.375.
That's nice. Okay. Third number.
1.2348.
Yep, and then you guys check to make sure that's correct. Buttons were missing there. Okay, and second to last.
I got 0.91592. 592.
So real quickly here, I don't think that would be nice.
Wait.
Uh-oh, can I say uh-oh?
Yeah, go ahead.
I'm gonna say uh-oh. Okay, let's go back. I'm so sorry. Don't throw anything out. Okay. This little X right here, that's not X.
Sorry, just wish to just chart.
I'm so sorry. Here's what we're gonna do.
I'm so happy I wrote
That's
it.
base. Sorry for that wrong again.
I was like, why do you think it's so nice?
That right there. That right there, not fun. All of it, but not all of it. This one right here is still true. This one was X times P. You guys give me those numbers real quick.
0.16. 24. 0.84. 0.80. And 0.70.
Thank you. 2.94?
Yes.
Yes, okay. Sorry. X minus mu is going to be, here it is, it's going to be 1 minus 2.94.
All right.
X value not equal. I'm sorry, Tristan. You're just gonna have one or two more questions like that, so hopefully you don't make the same mistake. So the X value is the 1, 2, 3, 4, 5, not the probability
First
quotients.
one is negative 1.94.
Okay? 2, and yeah, this one should be easy because that one's just gonna be one less than the other one, right? The backside is gonna be 3 minus 2.94 should be a 0.06. And then this one should be that should be all easy here, 1.06, 2.06, because you're just subtracting from one each time or adding one each time. Okay, there's that, thank you. Okay, really quick. Can we do X minus mu and square each one of these guys? Sure. Okay, I'll square away.
3.76.
Thank you.
.8836.
Thank you. Oh, 0.06, that's going to be 0.000036, I think. Maybe 36 with 2 zeros in front before the decimal point. Okay. 1.06 squared.
1.1236.
And 2, somewhere in the 4s probably. 2.06 times.
4.2436.
Okay. That's the square form. Okay, now the third column, which I'm going to make on the next slide because I'm running out of room, this is going to be now X minus mu squared times your probability. So it's this column multiplied with this column.
Okay, so the first one.
Sure. Let me make the new slide here real quick. Keep that one. Got to get rid of that one. And jump to presentation. Okay, so this is now. X minus mu squared. Sorry, Tristan. 35 minutes of your life just for nothing.
For real?
Sorry, man. So multiplying the last column and the probability.
Oh, it was 0.602176.
Thank you.
.194392.
Okay.
So I got .001008.
Awesome.
.22472.
Yeah, I'm going to add an extra little 0 here because all these guys have 1, 2, 3, 4, 5, 6 decimal places of accuracy. So I'll add that in. And one last one.
459, 4104.
Perfect. Okay, so this is gonna now do the summation. Okay, summation of this guy.
So to get this is you multiply it by 766 times. What it was.
To get this guy here,
Yes.
yeah, it was, yeah, 3.7636 for the first one. Times 0.16. So,
Just tells you.
Yeah.
1.6164.
1.6164, perfect. Okay, that summation is going to be the variance. So that's this guy here. So then standard deviation is going to be the square root of that number there. So the square root of 1.6164 is going to be 1 decimal place accuracy.
Just 1.
1.3. The reason for it is because we have discrete data and they're all there's 1, 2, 3, 4, 5, right? So in order to get accuracy, we just go one level deeper. It would not make sense to be at 1 and 1.3 something other does not have us. So if we think back, okay, so let's think about this. So just for a little bit, let's wrap a few things together. If you guys think back all the way to, remember this little curve right here? Right? Remember how we talked about if this is the mean, and we take one standard deviation both directions. We go 1s this way, 1s this way. That means 34% of the data here, 34% of the data here. So kind of like roughly speaking, we have about 70% of the data, right? In that. So we're saying the majority of the data, right? Because 70 is a good number, right? Of the data. So we're saying from the 2.94, if we add 1.3 this way, or we subtract 1.3 this way, most of the 150 people fell right into that little category there. That's how much spread we have in this data. Are we good? Okay. That is standard deviation of discrete probability data. Oof. You don't have too many of those to do alone. That's a good thing. Okay, next. Yeah, before. Say again. Is there what? Break, yes. We just have to do one thing real quick here. Just one. It's like, thank you for reminding me. Because I get too excited about mathematics. Forget about breaks. You've seen, okay, gotcha. Oh, you did too? Okay, that's cool. Okay, guys, one more thing to do before we finish up. 4.1 is something called expected value. This is something that works actually in the lottery quite a bit. So if you have some probability of winning, some probability of losing, is it worth your time and investment into this? So it's something called expected value. Let me jump to it. Come on. So the definition, and we'll do a quick example here. Equal to the mean. And the formula, there it is. That and the formula. So expected value of a discrete random variable. It's equal to the mean. So basically what it says, what we're really doing is we're just getting the average. And once we get the average of something, we figured all the ways we can win. We figured all the ways we can lose. And at that point, then we figure out what is the value. And we'll fill out a table in 1, 2, 3, in 3 slides. We'll fill out the table. The next 3 slides are really just describing the situation.
What was the,
Mu. M-U is the pronunciation. M and U together. And mu is the average for the population, right? The mean of the population. We have all the information on this. Okay, let's jam. Almost done. So here's what we got. So we're still writing it out. Go for it. Cool. So here's what we got. We have ourselves a raffle drawing here. So we have 1,500 tickets that are sold. They're $2 each. Don't need to write it down. We're good. Just kind of work through this here. You guys will have a home section. All right, the prizes are, here it is. The prizes are, there's a $500 prize, a $250 prize, a $150 prize, and a $75 prize. You buy 1 ticket. So the question is this, find the expected value of this situation. So is it worth it, not worth it? We'll see. Let's go. So if you write this all out, so let's see, your gain. So if you were to buy that 1 ticket and you actually win the $500 prize, that means you've gained, because you already lost $2, right? You gained $498. Likewise, you go down the list, your gain for the 250 is 248, then 148, and then $73. Okay, these are important because that's actually what we're going to win after everything's said and done. Okay, so if that's the case, one more thing. What happens if you didn't win anything at all? So 0 minus 2 means you've lost $2 in the process. We good? Cool. Let's go with it here. So if there's 1,500 raffle tickets, right? So here it is. Your gain is your X value. And this one. I'll let you guys, let's see, we'll put this together in just a little. So we are going to take this guy, it's called the X, multiply it times the P of X. And we're going to add it to this one, add it to this one, add it to this one, and this one. And what we get at the end will be our expected value for this drawing. Okay. So we go back up here. We look real quick here. So go back to the formula definition, right? Because that means this right here. We're adding the X's and the P of X. Once we multiply those guys together, we just add them up. But this one, though, it's pretty easy because all we do here is notice that everything is divided by 1,500. So it's really, if you calculate, if you want to do it on a calculator, just put 498 divided by this plus 248 divided by this. 148 divided by 1,500, 73 divided by 1,500. This is the tricky one here. So it's plus, or it's minus here, minus. It's going to be 2 times 1496 divided by 15. And so what's the expected value? I'll just tell you, and then you guys calculate your break if you want to. If you were to do this, calculate it out, you get, for this particular drawing, it's $1.35 in the hole. That's kind of what your expected value is, which means you can expect to lose $1.35 on the ticket plot. Are we good? Now notice if the prize was bigger, right? If the prize was bigger, that number would change, right? And then we have ourselves in, is it worth it or not? Right? That's the question. Is it worth it to buying into raffle ticket or not? Okay, I'm gonna stop there. It is break time. I'm gonna go. Let's go all the way to 1:40. So an extra minutes just to cool down. Not 10 minutes. How about 14 minutes now? You feel very scared. All right, let's jam with it here. So that was 4.1. 4.1 was same stuff we did in chapter 2, right? But this whole concept of discrete probabilities. Let's go now to something called binomial distributions. Okay, again, weird fancy words here, but binomial just means two. Okay, distribution means you can distribute something, but it only has two parts, right? So this one, it's not discrete as individual pieces, right? Now it's just like you only have choice, two. Success, failure, right? That's kind of your two choices. Choices heads or tails. That's kind of what we're looking at. And so let's jam with it here. So, let me see my little notes here. Okay, what's that? Not sure if you want to write this one down or not. This is kind of like for you guys. So kind of 4 different properties of binomial distributions. First things first is you get to repeat this thing for a fixed number of trials. So 3 different pennies, right? 3 different trials, and you're done. There are only 2 possibilities for this thing to happen. We technically just say success or failure. That's good. So if you try to get heads, heads is your success, tails will be your failure. So then you got probability of success, P of S, will be your success trial, and then we got to figure out the randomness of it. X is going to be the number of successful trials. Okay. So some variables. These you probably want to write down. So you guys have some variables in front of you. Just kind of say them, you'll know what they mean. So whenever we say n just means the number of trials that have to be. 4 trials, 6 trials, 10 trials. Probability is the success at that single trial. Q would be the probability of failure at that single trial. So then let's talk about this here. So if 25% of the time that you are successful, you subtract this from 100, that was 75 if you are unsuccessful. Right? And so this with probabilities, we're in decimals. So if 0.1 or 10%, 0.1 is when you're successful, 0.9 is when you're failing. And then X would be the count of the number of successes. Just waiting for you guys to go down. So whenever you see a variable, you're not confused as to what the variable is. Yes, we'll take that. So binomial just means 2. So we have a binomial distribution, distributing things in regards to 2 outcomes. And so the best way to do that is talk about heads and tails, right? Here we're going to talk about success or failure. So success is one probability, failure is another. And so now you got yourself in a way. It's just a yes or no. Let me go back and we'll come back to this one just for a second. Here, 4.2 Binomial Distributions. Section. And then next slide, let me write it down. So this is a fixed number of trials. We did so many times. So 3 coin tosses, let's say. The outcomes have to only be 2. Also outcomes, so we talk about success and failure. So outcomes, POS, probability that you're going to have a successful outcome each trial. And X is going to be the numbers. This part right over here. Talk to me, everybody else, good there, this one? Okay. Let's do an example, just real quick here. Just setting up our variables. Don't need to write it down, just kind of let's think together. So decided which experiment is binomial. If it is, then can you give me the n value, the p value, the q value? So a certain surgical procedure. Whoa, that's not false. That's weird. Okay, hold on. A procedure has an 85% chance of success. Okay. Doctor performs a procedure on 8 patients. So the random variable represents the number of successful surgeries. Ooh, okay, you guys talk to me. What in the world is n? I go back to this. Perfect. At this point, how many? 8. Right? I'm going to perform the surgery 8 times. Okay. P, what's my p value? Well, so I'm looking for the correct answer still. It's not 85%. 0.85. Good. So always start right with a decimal. Q value. What's the Q value? Point 5 or 0.15. It's going to be the number subtracted from 1. There's that. And then the X value is going to be anything from 0 to 8. So there it is. Okay. And are we good with those numbers there? So I should go here. Boom. Okay. Jam. Okay, these we got the numbers identified. Any questions on those numbers? Oh, okay. Goes Jam. This one. Talk about, is this a binomial experiment or not here? Decide whether it is. And if it is, then I need the NPQ values. The jar contains 5 red marbles, 9 blue marbles, 6 green marbles. You randomly select 3 marbles of jar without replacement. The random variable represents the number of red marbles. Trying to figure out how many red marbles we would pick out of this. The problem is this guy right over here, the little guy that says without replacement, right? So when you pick 3 marbles, right? When you pick the first one, the probability has already changed from the previous one, right? If we were just trying to get red marbles and it was with replacement, we pick it out, we put it back in, pick it out, put it back in. That would still be a binomial experiment. Right? Just the fact that we're without replacement, we're just picking 3 out. That does not make sense. Okay, big numbers here. Don't get too scared. Let's look at this formula. So the success for formulas is this guy right here. We've seen that combination before, right? That little n c of x before. So let me do this here. I'm going to do it the long way first. Don't copy me. It's the long way. And then we'll do it the formula way, which makes a lot of better sense. And is a lot easier. And doesn't take half a day. Again, pretty cool formula. It takes a while to figure out how come that is true, but let's see if we can do just a little bit. You guys remember this little part right here? That's your C value. Remember this one? It's all the different ways something can happen, right? That's from Tuesday's class, yeah? All the combinations that things can happen. So that's the multiplier. And then P is going to be all the times that success has come into the play. All the times we were successful. Q would be all the times we were not successful. There's kind of what you're looking at. So the formula, it makes sense if we see it what it is. All the different ways things can happen. Your probability that it was successful, probability it was unsuccessful, and we multiply those guys together. So it's done. And yes, we'll either calculators to punch the same in just a bit. Let's see this. I'm going to go with, don't need to write this down. Let's just do it together here. So rotator cuff surgery. Anybody had a rotator cuff surgery before? Anybody know what is a rotator cuff? You health science majors, come on. Let's say again, Tristan. Uh-huh. And usually we talk about rotator cuff right here, where where your arm is, and arm, I believe, Tristan, it is true, right? Your arm, your shoulder is the only one that actually has a rotator cuff because it has this little ball in the middle.
Yeah.
And you can spin it pretty much 360 degrees all the way around, right?
Yeah.
That's kind of what allows you to do that. And it's so cool how your nerve endings are actually right in the center of it, so your nerve endings never spin because they're all in the same spot still. It's cool. It's awesome. I should look back. Okay. So rotator cuff surgery has 90% chance of success. Good doctor. Hopefully stays that way. Okay, the surgery is performed on 3 patients. Okay, so now the question is find the probability of the surgery being successful on exactly 2 patients. Did you guys like this kind of makes sense? Like surgeries can go unsuccessful. Okay? So I'm thinking if I were to have surgery, I would shop for the doctor that does it all the time, can do it in sleep, right? That's the doctor I want, right? Like not like, okay, well, sure, let's go. Cut my arm open. Okay, so let's do this here. Let's do it the long way. Don't do it the long way, right? So here's the long way. So I have 90% success rate, 10% failure rate, correct? I'm doing this 3 times. Here's the long way of viewing it. So success versus failure, first time around, or the first guy, then comes the second guy, and then comes the third guy. So if 90% is the correct probability, so it would be 3 successes. It would be 9/10 times 9/10 times 9/10. You guys talk to me. Are we okay with those numbers? Uh-huh. So if this is so interesting, so if he performs 3 surgeries, right? His success rate actually goes in for all 3 successes, right? His success rate goes down to about 72.9. Everybody's gonna have all 3 surgery successes. Okay, so let's do the top of this one. SSF. So this means 2 successes. The first 2 are successes, the last one's a failure. Sorry for that guy. We get 81 out of 1,000. 2 successes. First and last success, second one, not good. Hey, that's weird. Look at this. These numbers are all the same. It's almost like if you just multiply this by 3, everything would be fine. Is that right? Interesting. Okay. So then the 1 success happens here, and the complete failure. So every 1,000 times he does the surgery, it would be like a failure. Okay. Good. Cool. That's the long way. I don't think you guys want to do a diagram, put all those numbers in, then add these guys up. So this one actually would be addition, is that right? No, multiplication would be this one plus this one plus this one. Or multiply by 3. Okay, the formula way. Forget this. Let's go the formula way. So if we were to multiply this guy by this, it would be 3 times 81, which is 243. We divide by 1,000, so he has a 24% probability of having 2 successful and 1 unsuccessful. Good. He has a 72%, almost 73% probability of having all 3 successful. Good. So good job. Okay, let's jam. Let's put this in. So using the formula that we just wrote on your notes, let's go with it here. So I have n trials, n surgeries are going to take place. The p-value is 9 over 10, so 9%, or 90%, sorry. This is 1 over 10, which is 10%. And then we're looking for x being 2, because that's the number of successful trials. Are we good? Can we do this before I give you guys the answer? Can you plug into those numbers into this formula right here? Like, think about which one is which, right? So we need the n number. At least write this one out, right? Because that's the one we're going to plug into our calculators just a bit. Just plug that one in. And if you want to write it out this way, that's fine too. So the n value, x value, the p of x, whatever that is. Then you can write it. You can write it as a decimal. That's fine too. If you want to write it as a decimal, write it as a fraction. That's fine. And the q values. Go back over here. You guys have this on your notes anyway, so I'm going to go back over here now. Right here. You write that formula with all those numbers in there. It's just a matter of putting the n's where the n's should be, the x's where the x's should be, the p where that should be, the q where that should be. Yes, sir.
I may or may not have to go back to the number. Second thing, we'll put the number under the.
Oh, yeah, put the number first. And we'll do the calculator in just a second. So you put the number first and then you go next. So n is 3 trials, we're good? Okay, so let's jump to our calculator. Let's look at the same number. Also the same number. So how you punch it in? Here it is, first of all, writing it out. So writing it out looks like, ooh, that's not good. I don't like that. Okay, so I have 3 C times 2. Right? And this is multiplication. So if you want to put the multiply symbol, multiply by 9/10 to be successful. So I need 2 successful trials. Multiplied by, I need 1 not successful trial. We don't like Charlie. We want him to not have a good one. So that means this is a 3 minus 1, so 1 unsuccessful trial. Are we good? You can write it like that. Fractions are good to go. If you want to write it like this, that's fine too. Right, because this is 0.9, right? 0.9, the second power multiplied by 0.1 to the first power. Okay, let's jump to our calculator. For sure, right? 2 seconds. All right, getting a calculator out. Back to here. It's okay, good, good, good. So let's punch this. Let's go here. So follow me, ready? Unless you did it already yourself, that's cool. So first things first, we're going to punch in a 3 first. And anybody, tell me, how did I get to that little weird menu with a C inside? That menu. Probability, so you go to the left or to the right. And number 3, so scroll down if you like, press enter, or just you can punch in 3. Okay. And then that's 2. And what I do, just because it's such a big thing, right? I would press enter right now. Let's just press enter right now because that's 3 there. So that means there are 3 different variations. Hey, anybody know where that 3 number comes from? On the previous slide, we were doing the long way. How many times did we multiply by? 3, right? Because there was 3 times. There was 81 over 1,000, 81 over 1,000, 81 over 1,000. Right? There's 3 different possibilities of 2 success rates, right? Okay. Then what you do is if you press times right over here, it'll bring up the answer before. Okay? So now we have ourselves. So now with the parentheses here, let's go 0.9 to the power of 2. So this little value over here above the dividing number, that's more power. It's called carrots. I don't know why they call it carrots. But technically it takes it to the exponent. Right, so that's the second value. Times by another parenthesis. I like parentheses because then I know exactly what I'm plugging in. Do I really need to put 1 power on there? Nah, 1 power is just 1 power, right? And let's check this out. And Mark said, and no, you guys did you guys get the same answer that we got the long way? What did you guys get? So there it is, 24% ish, right? 24.3% is what's going to happen. Awesome, which is the long way, which would have been. Notice what's happening here. So the 3 comes from the combination, right? There's 3 different combinations this can happen. The reason, oh, talk to me. How come this is a combination as opposed to a permutation? From last time. Combination, permutation. I don't know. Yeah, go ahead. Yeah, combination means order does not matter. We're just picking 3 things. Permutation says order does matter. 1 is very different from 2, very different from 3. Order matters for permutation. Perfect. Yeah, the successes didn't matter which order they came in, right? It was success, success, failure in the first one. Success, go to success, and then go to success. So there it is. Your combination came from this little guy saying that there's 3 of these guys. Then notice 9 over 10, right? How many 9 over 10s do we have here? We have 2, don't we? Look at that. 9 over 10. Then we have 1 over 10. This one has 2 9 over 10s. 1 over 10. This one has 2 9 over 10s in the last. And this has 1 over 10 at the end. Good. So all the stuff comes from right from those numbers right there. Because part of making mathematics is like figuring out okay, that's where it comes from. That's what's like. Here's your formula, plug in, figure out what this how it works. Go ahead. And that's not what it does. Okay, doing it the long way here. Oh, sorry. Before calculators, before you had a TIE3 calculator, I should say this. Okay, just want to show you this here. So before you had the TI-83 calculator, 2000, I think, 19, yeah, about 2000. I think the TI-83 came in late 90s. No, it was 90s. That's right, 1990. So before then, what you had to do is you had to do it like this right here. You have to multiply this out. 3 factorial. 3 minus 2 is 1 factorial. We don't care about that. And then these guys were reduced down to like a multiplier for 3. These guys will multiply together here, and then you eventually find it. How many are like in your calculator now? I like now. Okay. Let's see. Should we venture this way here? Okay, next one on the list here. Okay, still talk about binomial, which is 2. We'll talk about 2 possibilities here. And we're just stacking stuff on top of other stuff here. So this is binomial distribution, but now we put in probability into it too. So it's those probability tables that we were just doing earlier. Okay, let's jam the rest of it. Let's let me give you 2 examples and then we'll do the third one. I think. So what does this mean? It means we're going to work with tables that looks like this. Again, don't write it down. This is what it looks like. Binomial probability distribution for a knee surgery. It's like this. So you've seen these tables before, right? Almost in the same numbers, haven't we? Right, 16. 14. So that's what it means. We're going to look at X values. We're also going to look at probabilities of success or failure. So again, don't write it down. That's just an example here. Let's walk through 2 examples, I think, and then we'll do the third one. So in a survey, US adults were asked to identify which social media platforms they use the most, I guess, or they use. The results are shown. 6 adults who participated in the survey are randomly selected. Asked whether they use the social media platform. Constructed by binomial distribution for the number of adults who respond yes. So, ready? So here it is. Adults were asked to identify social media platforms they use. So this is already data we have, right? So 68% use Facebook, Instagram, Pinterest, LinkedIn, and Twitter. Now we have this. We have 6 adults who participated in a survey are randomly selected. Ask which platform, whether they use Facebook or not. Right? That's the question. You guys remember MySpace? Anybody remember that? That is so funny. No one uses that now. MySpace, remember MySpace? Anybody remember that? I had one. Absolutely, I was cutting edge. I already forgot. Okay, so let's go. 6 US adults are doing this here. They're asking whether they use Facebook. Let's see what makes sense here. So, isn't P going to be 68? Yes. Is Q going to be 32? Yes. The number of adults asked? 6. All the different values. So it could be that 0 say yes. 1 of them says yes. 2, 3, 4, 5, or 6. Ooh, see if this makes sense, guys. 6, right? Success rate is 0. 0 asking, so that means you have 0 saying yes. You have 6 saying no. And then if you multiply that out, you should get very, very low. Then you got the next group. This is 1 of them saying yes. 2 of them saying yes. 3 of them saying yes. 4 of them saying yes. 5 of them saying yes. And 6 of them saying yes. Interestingly, where's the highest probability here? Say again, Tristan. Okay, gotcha. So this is, remember the little formula that we just did? It's this little formula all over again. So let me back up just a little bit, see if this makes sense. A lot of times, surveys done, right? Here's your survey. This is the truth of the survey, right? We survey these adults. A lot of times what happens is we'll go in and saying, if this is true, if that stuff is true right there, then we should ask. Notice 6 adults is not a good sample space, right? But if those values are true, if I ask 6 adults if they use Facebook, they should be able to confirm that that's what the study was all about. The study was good. So it's almost like a back view of seeing if this is true or not. And so let's, how about this, let's go through 1, 2, and then maybe by the third one, we'll see how we're doing. As if kind of just sunk in. Do it that way here. But again, don't want to lose you. So this is survey done. Let's say they asked like 12,000 people, right, in the survey. 12,000 people survey was done. It's like, this is exactly what's happening. And so for marketing, this is super duper important. Is that right? So if you're West Coast College, where would you market? On Facebook, right? If you want to sell something, where would you market? Facebook store, right? So if that's the case, right? And so now the question is this kind of true? Does this make sense? Does the data make sense? So what they do is they ask 6 adults and say, hey, can you participate in this survey? Tell me if you use Facebook or not. And so here's all the different possibilities that can happen. So the p-value, here's the math behind it, right? Facebook, according to the survey, 68% of them use Facebook, right? So if I were to ask these people, 68% of them should say yes. 32% of them should say no. And then there's 6 people that have been asked. So I'm just going to number crunch, plug into the formula that we used to do before. So here's our little formula that we did on our calculator just now, right? Again, just going through the motions. We'll get to the third one, we'll actually do it together. So 6 people interviewed. The probability that all of them say 0. All of them say they don't use Facebook at all. So there it is. It's the combination. Probability of yes and probability of no. Okay, let's kind of let that sink in just for a little bit here. Probability that one of them, and you don't need to write this one down. This is not a write down one. We'll do another one just a bit. So the probability that 4 of them will say yes is the highest one. So 32% of the people interviewed probably should say yes. If this stuff is skewed a little bit, let's say like 80% of the people you interviewed right over here, and they said only one of them says yes. Like that means the data. Someone did some funny stuff with the data that way. So it's almost like a back in door on this stuff. Okay, so let's take a look at this here. Notice that you go through these. Hey, that's interesting. Is this we got back to a binomial distribution. We got back to a discrete probability over here, didn't we? That's cool. There it is, discrete probability, because I have all these guys are under 1. And if I add them up, they give me 1. So that is so cool. Okay, let's do one more. One more, just to think about it, not to do it. Okay, so we found that 26% of US adults believe that there is no difference between secured and unsecured wireless networks. Secured network barriers or firewalls, passwords. You randomly select 100 adults. What's the probability that exactly 35 of the adults believe there's no difference in secured networks? I can't imagine it's that high nowadays with everything. But it says University of Phoenix. So University of Phoenix did this study, and the published date of this book is what, 2019? So I assume it's like maybe like 2016, 17 study. Okay, so again, we're just punching in the formula. This one I just want to show you. There's a whole bunch of different things that we do to do this stuff. There's something called Minitab. Minitab, what you do is you put exactly the numbers in. You say 100 people, your p-value is 26, and you put in x equals 35 and spit the data for you. Again, on Excel, how you punch in because they have formulas. Oh, hold on, what? Wait, hold on, look at this. It says binomial PDF. That's a TI-84 calculator. Don't we have TI-84 calculators? So hold on, 100.62. What is this? So how many people are there? Is that right? Probability of success, is that right? And the number that you want out of the mix as well. That is so cool. I think we might just use that. So real quickly here, let's find that in our calculator. You know what? Actually, no, we got to stop. Okay, let's stop here due to time. we'll pick up here next time. So we're gonna jump to this little thing right here. New stuff on our calculator. Just, I'll come back to that next time and we'll kind of rehash the things.
I'll
So-
shoot you.
Issue. Okay. So class.